Okay, so we just did part A. Part B is definitely worth doing first, as I said. Determine the radius that will minimize the surface area. So when you see a word minimize or maximize, you should be thinking optimization, which means differentiation, because we are looking at this equation, we're looking at this function. So the function's maybe doing, I don't know, something like this. There are peaks and troughs. We are trying to find, for minimizing, we're trying to find the trough, and for maximizing, we're trying to find the peak. And to do that, we need to differentiate and say, well, I know that the gradient will be 0 at that point, and that's the process, okay? So we're looking to differentiate, see where the equation equals 0, i.e. where the turning point is, and then prove by looking at our nature table that it is a minimum or a maximum, and that's pretty much it, okay? So, determine the radius, it will minimize the surface area. Notice not asking for the minimum surface area, it just wants the radius that will minimize it. So that's part of it as well. So the first thing I'd be doing is writing down my equations. So get your equations down. So I've got A with respect to R, 2 pi r squared plus 900 over R. Now I'm going to write that down in the non-friendly kind of substitution way, but the good for differentiation way. 900 r to the negative 1. And now I'm going to differentiate. So it'll be a dash with r. So what happens here? We'll just think of something nice and easy. So let's say y is equal to 3, not 3x, x cubed. That would become 3x squared. Okay, so we're just multiplying and then taking away 1. Okay, so you might want to just write that down just to remind you. Dead easy to get them mixed up. Okay, so I'm multiplying the powers and then I'm taking away 1. Multiply the power and the coefficient. So that's going to give me 4 pi, because 2 pi is just a number, isn't it? If it was 2, just 2 on its own would be 4, and so just 4 pi, pi stays where it is. Take away 1 gives me the r. That's negative 900, and if I take away 1, negative 2. And I'm just going to write that out nice as well. So a dash r. So that's still 4. Just to help me in case I need to substitute in. I like just getting this all done at the beginning. R squared. And I'll double differentiate, and that's what I do for my nature table. So this is a bit like saying, 4r. So that would just become 4 pi. The coefficient would stay the same. The r would disappear. See how the power is going down to 1 and then nothing. And this one is going to be plus 1,800, because 900 times 2, and take away 1, r to the negative 3. So my double dashed is going to give me 4 pi plus 1,800 divided by r cubed. And you should spot some nice patterns, plus, negative, plus. We see the power going down the way. That number, just same sign, is doubled now. Yeah, so you should see some nice patterns as well. So that looks okay to me. So we've got our equations now. Now I'm looking to differentiate. So I'm going to write down my stationary point. Okay, so first thing I would say is that a dashed r will be equal to 0 for a stationary point, or for a turning point, or a stationary point. So just let your marker know what you're thinking. So let's take my function then. So I'll say that 0 is equal to 4 pi r, take away 900 over r squared. Notice I've used this equation rather than this one. This is nice and friendly to rearrange. Okay? So I'll add that to both sides. So I've got 900 over r squared is equal to 4 pi r. So that means that 900 is equal to 4 pi r cubed. Scroll down a bit. So then r cubed is equal to 900 divided by 4 pi. So if I do the cube root of that, I'm going to get, well, actually, I'm just going to take that up slightly and just write that that's the cube root of 225 divided by pi. Just going to write that, which is the same as 4.15. So all I've done there is just done 900 divided by 4, and then it's the cube root. So the 4.15, that's the value of r, where I've got my stationary point. The marking scheme has left it as like this, but I think it's okay to just put that down as a decimal. So that's you've got your stationary point, and you've got your equations. Very good. Now at this point we just want to prove that this is in fact a minimum turning point. So that's where I'm going to use my other one. So I'm just going to say the nature, over here, the nature. So for the nature, the double differential will be greater than 0 for a minimum turning point. So I always think it's a bit like, what's the number in front of your x squared? Like if it's the number in front of x squared positive, you get the minimum turning point like that. Where you've got a number less than 0, it's a bit like, if your number in front of your x squared is a negative, that's going to give you a maximum turning point. It's going to give you the sad face. So that's how I remember it. So let's substitute that in then. So I've got a double dashed. I'm going to substitute in my 4.15. So that's equal to 4 pi plus 1800 divided by 4.15 cubed. So that number there is going to be greater than 0. So therefore, it's a minimum turning point. Now, you don't have to actually solve that. You can just, I think it's fine just to say, you can put a number if you want, but it's clear that's going to come out as a positive number. And that is you finished. You just want to do the final, I always just say a wee space for the final answer. Because sometimes it might have said what was the area then, and you would go and substitute your R value in, but we don't want that. We just want the value of R. So I would say, therefore, there's the minimum area when R is equal to, and at this point we could use the proper thing, we say the cube root of 2225 over pi. Okay. But just something that says you understand, what the question is asking. Some people would go ahead and substitute in. I think you'd lose a mark for that if you then said, well, the minimum area is whatever. It's not asking for the minimum area. It's saying what's the radius, and we've solved and said, well, that's the minimum radius. There's a turning point at that point, so we know that's one of the values. And just double check, yes, it was indeed a minimum turning point. So we just put those two things together. Okay, so a nice couple of marks for that one. And if you just kind of look at the process, it's not as hard as it might seem. And honestly, these things are very similar each year with the type of layout of the equation as well. So get your equations down, do your differential, double differential, put your differential equal to 0, and then rearrange to work out the value that gives you the minimum. Just double check, is it a minimum or not? Some people might want to use a nature table, that's fine. I quite like this method because it's just like one little equation, and then answer the question. Okay, so you've got your equations. I'm just going to put that in a box. You've got your equations, you've got your stationary point, you've then got your nature, and then you've got your final answer. Okay, so 1, 2, 3, and 4. 4 steps. And if you think on that process, it's not as scary. And that's why I quite like doing all the equations here, because it saves you here having to go back and differentiate again. It's better doing it here than differentiating for the first time here. Just do all your differentiating, and then you're following through the process. Okay, so 9 marks all in for that. It's a great question to learn, especially when you get the first bit. But like I said, don't stress too much about the first bit. Just make sure you read the question, you answer it properly, and you take your time with it, okay? I'm going to have to check to see if it would be okay to finish your answer 4.15. I think it would be okay, but I'll go and check that.